AMT Powerplant 1-2 engine components. Connecting rods are pivotal in transmitting forces between the piston and the crankshaft. They need to strike a balance between strength and lightness to handle loads without adding excessive inertia forces when the piston changes direction. There are 4 types of connecting rod assemblies explained in Figure 111. Plain, fork and blade, master and articulated, split type. The master and articulated rod assembly, often seen in radial engines, comprises a master rod linked to one cylinder's piston in each row. The other pistons in the row connect to the master rod via articulated rods. The articulated rods, usually I or H-shaped, are forged from steel alloy and contain bronze bushings for knuckle pin and piston pin bearings. The master rod functions as the link between the piston and crank pin. Knuckle pins attach the articulated rods to the master rod via flanges around the big end. A piston pin bushing, known as a plain bearing, sits in the piston end of the master rod to hold the piston pin. In engines with split spline or split clamp crankshafts, a one-piece master rod is used. The centers of the knuckle pins follow an elliptical path rather than a true circle due to the offset nature of the knuckle pin holes in the master rod flange, affecting piston motion. This variation can impact valve and ignition timing. To counter these effects, methods such as offsetting the knuckle pin holes and using compensated magnetos with breaker cam lobes matching the cylinder count are employed. This compensates for the irregularities in piston position during engine operation, discussed further in Chapter 4 on engine ignition and electrical systems. Knuckle pins, solidly built with oil passages for lubrication, are either fixed or full floating, allowing or restricting rotation in the master and articulating rod flanges. Lock plates prevent lateral movement. Plane-type connecting rods are common in inline and opposed engines. They use a cap and 2-piece bearing at the crank pin end, maintained in place by bolts or studs, ensuring proper fit and balance by replacing rods in the same cylinder and relative position. The fork and blade rod assembly, prevalent in V-type engines, accommodates a blade rod between forked prongs at the crank pin end and employs a single 2-piece bearing on the crankshaft end. However, this rod type is less prevalent in modern engines. Pistons. Pistons within a reciprocating engine are cylindrical members moving within steel cylinders. They function as moving walls within the combustion chamber, drawing in the fuel/air mixture during their downward movement and compressing it during the upward stroke. This compression leads to ignition, and the expanding gases drive the piston downward, transmitting force to the crankshaft through the connecting rod. On the upward return stroke, the piston expels exhaust gases, initiating the cycle anew. Regarding piston construction, most aircraft engine pistons are machined from aluminum alloy forgings. They're typically grooved to hold piston rings and contain internal cooling fins for improved heat transfer to the engine oil. These pistons can be either trunk or slipper types, but slipper pistons, lacking adequate strength and wear resistance, are obsolete in high-powered modern engines. The piston head may be flat, convex, or concave, sometimes recessed to prevent interference with valves. Modern engines employ cam-ground pistons with a larger diameter perpendicular to the piston pin. This design maintains piston alignment during warm-up, minimizing potential piston movement within the cylinder due to temperature changes. Pistons have grooves for compression and oil control rings, usually 6 in number. The upper 3 grooves house compression rings, while the oil control rings sit just above the piston pin. Holes in the oil control ring grooves allow excess oil scraped from the cylinder walls to return to the crankcase. An oil scraper ring at the piston skirt's base prevents excessive oil consumption. The piston pin, connecting the piston to the connecting rod, is typically a tube machined from nickel-steel alloy forging. It's case-hardened and ground, allowing free rotation in both the piston and the connecting rod piston pin bearing. To prevent scoring of the cylinder walls, a soft aluminum plug in the pin end offers a good bearing surface. Piston rings, integral in preventing gas pressure leakage and oil seepage into the combustion chamber, fit into piston grooves, Figure 115. Most piston rings made of high-grade cast iron are ground to shape, split, and then fitted onto the piston walls. They need to snugly fit the cylinder wall, exerting equal pressure for a gas-tight seal. Compression rings placed below the piston head ensure combustion gases do not escape during engine operation. Oil control rings below the compression rings and above the piston pin bores regulate the oil film thickness on the cylinder wall. Too much oil in the combustion chamber can lead to carbon buildup, causing various engine issues. The oil scraper rings, usually with a beveled face, positioned at the bottom of the piston skirt. Installed in a specific orientation, these rings manage surplus oil above the ring, ensuring its return to the crankcase during the piston's downward stroke. Cylinders. The heart of an engine where power is generated is the cylinder, figure 116. It acts as a combustion chamber for gas expansion and houses the piston and connecting rod. When designing the cylinder assembly, 4 crucial factors must be considered. Strength to withstand internal pressures. Use of lightweight metals to minimize engine weight. Effective heat-conducting properties for efficient cooling. Ease of manufacturing, inspection, and maintenance. Cylinder heads in air-cooled engines are typically aluminum alloy, chosen for its heat conductivity and lightweight nature. These heads are often forged or die-cast for added strength, adopting a semi-spherical shape for better strength and efficient exhaust gas scavenging. Air-cooled engines generally use overhead valve cylinders. Assembled in 2 main parts, cylinder head and barrel, a heated cylinder head is fitted onto a chilled cylinder barrel, resulting in a gas-tight joint. The head typically contains intake exhaust valve ports, spark plugs, and the necessary actuating mechanisms. Cylinder heads are equipped with spark plug bushings, valve guides, rocker arm bushings, and valve seats after casting. The valve guides and spark plug openings use materials like bronze, steel, or helicoil inserts for durability and functionality. The cylinder heads require significant cooling fin area due to extreme temperatures during engine operation. These fins, varying in thickness and depth, help dissipate heat effectively. On the other hand, cylinder barrels, where the piston operates, demand high-strength materials, often steel alloys with hardened inner surfaces to withstand wear from piston movement. Nitriding is a common process used to harden the surface, and cylinders can be repaired through processes like chroming and honing. Cylinder numbering and orientation in engines vary. In inline or V-type engines, cylinders are usually numbered from the rear. In opposed engines, cylinders might be numbered from the rear or front, and single-row radial engine cylinders are numbered clockwise when viewed from the rear. For double-row engines, odd-numbered cylinders are generally placed in the rear row, while even-numbered cylinders are in the front row. The numbering can differ between manufacturers, so consulting the specific engine manual is essential to understand the numbering system used. Firing order. The firing order in engines is a specific sequence for the power event across cylinders. It aims to balance and minimize vibrations. In radial engines, the firing order has a distinct pattern, aligning with the crank throws motion during rotation. Inline engines often have evenly distributed firing orders along the crankshaft. For instance, a common 6-cylinder inline engine fires in the sequence 1-5-3-6-2-4. In opposed engines, the firing order is listed in cylinder pairs, each pair firing across the center main bearing. A 6-cylinder opposed engine typically follows the order 1-4-5-2-3-6, though it might vary between models such as 1-4-2-3 or 1-3-2-4. For single-row radial engines, odd-numbered cylinders fire successively followed by even-numbered cylinders. In a 5-cylinder radial engine, the sequence is 1-3-5-2-4, and for a 7-cylinder radial, it's 1-3-5-7-2-4-6. In a 9-cylinder radial engine, the firing order is 1-3-5-7-9-2-4-6-8. Double-row radial engines have a more intricate firing order where impulses alternate between cylinders in different rows. 2 cylinders in the same row never fire consecutively. For a 14-cylinder double-row radial engine, a method involves starting with any number from 1 to 14, adding 9, or subtracting 5 until a number between 1 and 14 is achieved. For example, beginning with 8, subtract 5 to get 3, add 9 to 3 to get 12, and so on. In an 18-cylinder double-row radial engine, the firing order numbers are 11 and 7. Starting from any number from 1 to 18, adding 11, or subtracting 7 iteratively generates the firing order sequence. For instance, starting with 1, adding 11 leads to 12, subtracting 7 from 12 results in 5, and continuing this process for all 18 cylinders. Valves. Valves regulate the entry and exit of the fuel-air mixture and exhaust gases in an engine. In aircraft engines, poppet valves are predominantly used, categorized by their shapes as either mushroom or tulip valves. These valves control cylinder ports via the intake and exhaust valve ports, opening and closing to manage the flow. Valve construction is crucial due to exposure to high temperatures, corrosion, and stress. Intake valves, operating at lower temperatures, are typically made from chromic nickel steel. In contrast, exhaust valves, facing higher temperatures, are crafted from more heat-resistant materials like nichrome, silchrome, or cobalt chromium steel. The valve head's ground face seals against the valve seat in the cylinder head when closed, usually angled at 30 degrees or 45 degrees. To enhance durability, materials like stellite or nichrome are welded onto the valve face. These alloys resist high-temperature corrosion and wear associated with valve operation. The valve stem guides the valve head and is surface-hardened to resist wear. The neck joins the head and stem, while the hardened tip withstands the valve rocker arm's impact during operation. A machined groove on the stem near the tip holds the split-ring stem keys, securing the valve spring retaining washer in place. Certain intake and exhaust valve stems are hollow, partially filled with metallic sodium, an exceptional heat conductor. The sodium's circulating motion within the valve dissipates heat from the valve head to the stem, through the valve guide and to the cylinder head's cooling fins, reducing the valve's operating temperature significantly. Intake valves typically have solid stems and flat or tulip-shaped heads. Low-power engine intake valves are usually flat-headed, while some engines may feature tulip-type intake valves with smaller stems or similar to exhaust valves but with solid stems and heads. It's crucial to note that while these valves might seem alike, they are not interchangeable due to their construction materials. Intake valves often have a flat-milled tip for identification purposes. Valve operating mechanism. In the proper operation of a reciprocating engine, precise valve timing is crucial. Each valve must open and close at the correct moments, maintaining the necessary duration and lift for optimal performance. Intake valves typically open just before the piston reaches top dead center, while exhaust valves remain open after this point. This intentional overlap, where both valves are briefly open, enhances volumetric efficiency and helps reduce the cylinder's operating temperature. The mechanism governing the timing of valves is the valve operating mechanism, dictating when valves lift off their seats and how long they stay open. The cam lobe's shape determines both valve lift, the distance the valve is raised, and valve duration, the time the valve remains open. Cam lobes often feature a ramp or step, a gently sloping portion facilitating the gradual engagement of the rocker arm with the valve tip, reducing potential shock loads. Figure illustrates typical cam lobes. The valve operating mechanism includes a cam ring or camshaft with lobes that interact with a cam roller or follower. The cam follower, often pushing a push rod and ball socket, actuates a rocker arm, ultimately opening the valve. Springs, positioned over the valve stems and secured by a valve spring retaining washer and stem key, play a critical role in closing each valve and restoring the valve mechanism to its original position. This coordinated system ensures the precise timing and movement of the engine's valves, contributing to its efficient and reliable operation. Cam rings. The valve mechanism in a radial engine operates via one or two cam rings, depending on the number of cylinder rows. In single-row radial engines, a single ring with a double cam track manages valve operation, with one track for intake valves and another for exhaust valves. This cam ring, typically a circular steel piece, features lobes on its outer surface forming the cam track. As the cam ring revolves, these lobes engage cam rollers, elevating the tappet in the tappet guide, ultimately transmitting force through the push rod and rocker arm to open the valve. In twin-row radial engines, an additional cam controls the valves in the rear row. Mounted concentrically with the crankshaft, the cam ring is driven by the crankshaft at a reduced speed through the cam intermediate drive gear assembly. It features two sets of lobes on its outer periphery, one set for intake valves and the other for exhaust valves, usually with 4 or 5 lobes on each track. The spacing and configuration of these lobes, along with the direction and speed of the cam ring's rotation relative to the crankshaft, determine valve timing. The method of driving the cam can vary. Some designs feature teeth on the inside or outside periphery of the cam ring, affecting its direction of rotation in relation to the crankshaft. A 4-lobe cam may be used in 7-cylinder or 9-cylinder engines. In a 7-cylinder engine, the cam rotates in the same direction as the crankshaft, while in a 9-cylinder engine, it rotates opposite to the crankshaft. The firing order in a 9-cylinder engine is spaced at 40-degree intervals, resulting in 80-degree gaps between firing impulses. However, the spacing between the lobes on a 4-lobe cam is 90-degree, creating a greater gap than the firing intervals. Hence, to synchronize valve operations with the firing order, the cam rotates opposite the crankshaft's direction in a 9-cylinder engine. Conversely, in a 7-cylinder engine, where the firing intervals exceed the cam lobe spacing, the cam rotates in the same direction as the crankshaft. Camshaft. In an opposed engine, the valve mechanism operates through a camshaft that is driven by a gear meshing with another gear linked to the crankshaft. This relationship, illustrated in figure, ensures that the camshaft always rotates at half the speed of the crankshaft. As the camshaft turns, its lobes prompt the tappet assembly to rise within the tappet guide, initiating a forced transmission through the pushrod and rocker arm, ultimately opening the valve. The tappet assembly encompasses several components. A cylindrical tappet that moves within a tappet guide installed in one of the crankcase sections around the cam ring. A tappet roller that traces the outline of the cam ring and its lobes. A tappet ball socket or pushrod socket. A tappet spring. This assembly's purpose is twofold: to convert the rotational movement of the cam lobe into reciprocating motion and to transmit this motion sequentially to the pushrod, rocker arm, and ultimately the valve tip, ensuring the valve opens at the precise moment required. The tappet spring serves to minimize clearance between the rocker arm and valve tip, mitigating shock loads when the valve is activated. Moreover, a passage drilled through the tappet allows engine oil to flow to the hollow push rods, ensuring lubrication of the rocker assemblies. Solid lifters, tappets. Solid lifters or cam followers commonly necessitate manual adjustment of valve clearance by tweaking a screw and securing it with a lock nut. This clearance is crucial to ensure the valve has adequate space in the valve train to fully close. Until hydraulic lifters were introduced, this adjustment or inspection remained an ongoing maintenance task. Hydraulic valve tappets lifters. Certain aircraft engines integrate hydraulic tappets that automatically maintain valve clearance at zero, obviating the need for any valve clearance adjustment mechanism. Figure showcases a typical hydraulic tappet zero-lash valve lifter. When the engine valve is shut, the tappet body, cam follower, rests on the base circle or rear portion of the cam. As illustrated in figure, a light plunger spring elevates the hydraulic plunger, causing its outer end to contact the pushrod socket, exerting gentle pressure that eliminates any clearance in the valve linkage. As the plunger extends outward, the ball check valve moves away from its seat, allowing oil from the supply chamber directly linked to the engine lubrication system to flow in and fill the pressure chamber. When the camshaft rotates, the cam pushes the tappet body and hydraulic lifter cylinder outward, sealing the ball check valve on its seat. Consequently, the trapped oil within the pressure chamber functions as a cushion. While the engine valve is off its seat, a predetermined leakage occurs between the plunger and cylinder bore, compensating for any expansion or contraction in the valve train. Immediately after valve closure, the necessary amount of oil to replenish the pressure chamber flows in from the supply chamber, preparing for the next operational cycle. Hydraulic valve lifters typically undergo adjustment during overhaul. They are assembled dry, without lubrication, and clearances are checked, often adjusted by employing push rods of varying lengths. Establishing a range for minimum and maximum valve clearance is standard. Any measurement within these limits is acceptable, although a value approximately halfway between the extremes is preferred. Compared to the screw adjustment type, hydraulic valve lifters require less maintenance, boast improved lubrication, and operate more quietly. Push rod. The push rod, tubular in shape, transfers the lifting force from the valve tappet to the rocker arm. Each end of the tube typically has a hardened steel ball pressed over it or into it. One ball end fits into the socket of the rocker arm. Sometimes the balls are on the tappet and rocker arm while the sockets are on the push rod. The tubular design is chosen for its lightweight nature and strength. It allows pressurized engine lubricating oil to flow through the hollow rod and drilled ball ends, lubricating the ball ends, rocker arm bearing, and valve stem guide. Enclosed within a tubular housing extending from the crankcase to the cylinder head, the push rod is housed in push rod tubes. Rocker arms. Rocker arms transfer the lifting force from the cams to the valves. As depicted in video, rocker arm assemblies are supported by plain, roller, or ball bearings, or a combination thereof, serving as a pivot. Generally, one end of the arm bears against the push rod while the other applies pressure on the valve stem. At times, one end of the rocker arm may feature a slot for a steel roller, while the opposite end may consist of a threaded split clamp and locking bolt or a tapped hole. Some arms incorporate an adjusting screw to set the clearance between the rocker arm and the valve stem tip, ensuring complete valve closure. Valve springs. Each valve is closed by 2 or 3 helical springs to counteract potential vibration or surges at specific engine speeds. Using multiple springs nested within each other allows different springs to vibrate at various engine speeds, effectively damping out vibrations during engine operation. Moreover, employing multiple springs minimizes the risk of weakness or failure due to heat and metal fatigue. These springs are held in place by split locks positioned in the valve spring upper retainer or washer recess, engaging a groove machined into the valve stem. Valve springs serve the dual purpose of closing the valve and keeping it firmly seated on the valve seat.